So just
Okay,
give
sir.
him a call if he can just because it is just just listening. You have
Okay,
don't
okay,
have to overtax yourself.
okay, okay, okay.
So can we start? So it's already 5 minutes past 10.
Sir,
Somebody left the meeting.
just wait
Yeah.
1 2 minutes. Hmm.
Hello, sir. You can start now because sir, Umesh are saying in Delhi, Kisan Pro. Hello, sir.
Yeah, I am hearing. Tell me.
हाँ सर, वहाँ पे मतलब किसान आंदोलन चल रहा है ना, दिल्ली एंड गुड़गांव में, तो वहाँ पे
Okay. Okay.
नेटवर्क।
Okay. So another thing that how we will be able to come for the because the exam will be physical exam. So does he have any plan to come here or he is asking to take it online or something like that?
Sir, there is
Are
no
you aware?
online. Sir, there is no online.
I
He has
I
to come out.
understand. Okay, okay. So he has to then plan because if the exams start in one or I think more than just after 1 week, I think 15th it starts. So he has to come anyhow. So it's
I think,
better to arrive early.
sir, sir, I
Yeah.
think the exam dates will be shifted.
Okay, shifted by a few weeks.
No, no, not few weeks. I mean 3 to 4 days, I think. I mean,
Acha.
what is the
Okay,
amount of shifting that we don't know, but we got some mail from COE, and due to Umesh,
okay,
as he is and outside of Kolkata, he is planning to shift it, and the final, schedule they will release in this week.
okay, okay. Because I have not talked to the COE regarding the exam because I didn't have time to because so maybe you better know about it. So when is the exam? I just received an email that I have to be because it will be a physical exam. So we all have to be there during the exam, and it will take in the unified campus. So that's the only message I received. But the dates, I think I have not received the dates. I don't remember receiving the dates. But there was some discussion in some meeting that it will be around the second week of February. Anyway, so let's start. So and I would ask you, because he is in trouble, so help your friend. So whatever I discuss here, you discuss with your friend, and if he has any problems, just he can contact me. No issue. Anyway, so let's just discuss the whole nuclear physics course. We'll try to finish the whole nuclear physics course, or maybe at least half of it revising, and leave you for your preparations for the GATE exam. It's better that way. So you can see my screen, right?
Yes, sir.
All of you?
Yes.
Okay, so we started with some historical perspectives when we started this nuclear physics lecture, and there were some years that I have written that which are sort of, I would say, the most important years in the development of nuclear physics. And you have seen what are the landmark discoveries that were done during these particular years, and who are the key persons, I would say, who are the key persons who contributed to the development of nuclear physics. It is better that you go through this once or twice, so that you remember how nuclear physics actually developed. There might be some easy questions from here, that who discovered, for example, artificial radioactivity, or who discovered neutron. Maybe there may be some questions asked from there, because you have to know the history of nuclear physics as it unfolded during the last century. Okay, and then we started studying the properties of nuclear physics. I am not revising the stuff about the recent developments in nuclear physics, like the nuclear halo, or whatever the new developments, because those are not part of your coursework. But I told you all those stuff to give you a perspective of what nuclear physics is today. I mean, it is a really interesting juncture, and I showed you this picture of our experiment at CERN, and how this nuclear physics has developed to, I would say, in a reincarnated way, to use radioactive ion beams and do very great nuclear astrophysics works and all that stuff in new context in this new century. So academically, we studied, the first thing that we studied is the size of the nucleus and alpha decay. So obviously you have to know how this de Broglie wavelength is calculated, and what is the typical size of the nucleus. Is it of the order of Fermi, and how it compares to an atom, which is about of the order of angstrom. And if for an relativistic electron, what will be the wavelength, and how would you estimate the radii of different nuclei. So those are the things. And also, like for mirror nuclei, you see the electrostatic energy that was produced by the addition of a particular proton, W equals 6 Zt square over 5r. So it is shown in appendix I. So you might be required to remember this, or you have to use this because if you remember this expression, then it's easier for you. But otherwise, you have to deduce it at your examination to do any problems. So it might be that some questions might come, like, say, for example, there are these two mirror nuclei. So what is the electrostatic energy produced by the addition of one proton, like that? So these are simple things that are required. What?
It is already asked, sir.
What is it?
It was given some two mirror nuclei. Yes, sir. It is already asked.
Okay. So you just remember those stuff, so those problems and all these things. Those are very important. For electrons also, if it's if it's a relativistic electron, how it can actually probe the nucleus size. So you can see that for that higher energy electrons, the lambda is of the size of the nucleus. So if the probe is of the size of the nucleus, then obviously that probe can follow the nucleus. That's it. Somebody left the meeting. Anyway, so although you have to understand what are mu mesonic atoms. So if you replace an electron by a mu meson, so what actually will happen to the nucleus and how the nuclear orbits, I mean how the mesonic orbits will be, what are the size of the orbits as compared to the electrons in a normal nuclei. Also, you have seen that this radioactivity, the theory of alpha radioactivity and what's the the potential at a large energy due to the Coulomb repulsion between a nucleus of charge Z-2. So once the nucleus emits an alpha particle, it remains that the charge of the nucleus is Z-2 because alpha particle has gone out of the nucleus, so its charge, the nuclear charge, reduces by 2, so it remains as Z-2. And the alpha particle has gone out of the nucleus, so the Coulomb repulsion between the two will be Z-2 into 2. That 2 corresponds to the Z of the alpha particle. So Z1, Z2 E square over R0. That's the potential energy. So obviously that creates some kind of a barrier. So initially, so the alpha particle cannot go out of the nucleus because of this barrier. So it has to tunnel through the barrier. And that tunneling probability actually gives you the lifetime of those kind of nuclei. And you can see that if the for thorium nucleus, the energy of the alpha particle that is emitted is 4 MeV, and for polonium it is like 7 MeV. So you can see that if the energy of the alpha particle is very high, so it is easier for it to penetrate the barrier, right? And so you can see it's of the order of seconds, 10 to the minus 4 seconds. But if the energy of the alpha particle is lower, like 4 MeV, it takes years, 10 to the 10 years to even go out of the nucleus. So these are the numbers that you should understand, that these are the things that actually determine the lifetime of those nuclei, how it will emit. Next comes the binding energy. So you have seen that the binding energy is actually the mass of the nucleus. You see sigma mi, the number of constituents minus the mass of the actual nucleus, and so you know that it's a positive number. So you can say, for example, if you are given the if you are asked to find out the binding energy of the deuteron, so how will you do it? So you will have the proton mass as 938.3, neutron 939.6, and electron mass 0.511, and deuteron mass is 1875.6 MeV. So basically, if you calculate, put them in this expression, so you can find out the binding energy of the deuteron. There are other things called mass excess and atomic mass units, but most important thing is the binding energy, which you should remember, at least the expression binding energy is equal to this, and it is a positive number. Then comes this electrostatic, that I already discussed, and this theory of alpha disintegration. I believe that all of you have at least gone through this expression at least once, but obviously nobody is going to ask you to deduce all these complicated expressions. So for this exam case, this is not very important to deduce all that stuff. You just remember what exactly is the phenomena, what is the physical thing that is related to it. Then comes the angular momentum and magnetic moment. So you have this total, the total angular momentum is the nuclear and plus the electronic angular momentum, and there are presence of several isotopic nuclei which leads to, these are connected with the different orientations of the nucleus, and you can see that this gives rise to hyperfine structure. So you might be asked what exactly is hyperfine structure and how it comes about. So this is important thing, and you can see that for nitrogen 14 the spin is 1, because initially there is this Plum pudding model, and then actually people understood that there is the nucleus within which there are protons and neutrons, and the electrons are outside the nucleus, and that gives rise to the nitrogen 14 spin 1. So experimentally it was observed, but if you consider the Plum pudding model and all that stuff, you won't get that spin 1. Then comes the magnetic moment mu, and you have seen that the proton magnetic moment is found out to be 3 times larger than expected, and ultimately it was found that the proton magnetic moment is 2.79 times the nuclear magneton, and the neutron magnetic moment is a minus 1.91. So it's a negative. And what is the significance of a negative magnetic moment? The negative sign means the direction of magnetic moment is opposite to the angular momentum. So you might be asked that why is the negative magnetic moment? So that's very important. So why the neutron magnetic moment is negative? And how come this Deuteron magnetic moment comes out to be 0.857? Though if you sum up these things, it comes out to be 0.880. So you might be asked that additive of the moments that can be assumed only if there is no orbital contribution. But for Deuteron, you have an orbital contribution. That's why it does not just additively give the Deuteron magnetic moment. So these are the important things. Then these electric moments, you just remember the expressions that these are the things how it was deduced. Nobody will ask you to deduce the multiple expansion and then find out all these things. But these expressions may be important for carrying out some problems. And also, obviously, if you just correspond it to the wave function, so basically these charge densities, those are converted into the probability densities. So you can have like Q is equal to ZD times integral of psi n mod square D3R, like that. And then we come to the magnetic moment. So it is just the similar extrapolation of the electric moments expression. You have the total magnetic moment given as as a EH cross 2mc plus the orbital contribution and the spin contribution. Might be required in some problems, just simple problems. Then we moved on to the Deuteron, and important thing is that you might be asked that why it is reasonable to expect that by studying the energy levels of two nucleon systems and by measuring scattering of nucleons by nucleons, the nature of the nuclear force could be determined. So that what you actually have to understand that historically what happened, that we knew the Coulomb force, studies of the energy level of the hydrogen atom led to the discovery of quantum theory. But in nuclear physics, it is exactly the opposite. In the nuclear physics case, we did not know the force. So ultimately, but we knew quantum theory. So when we studied the bound state of the deuteron and the nuclear scattering, quantum mechanics was known. So these informations will lead to the study of the nuclear forces. It is just historically, it is just we address the problem just in the opposite direction as we did for the Coulomb force, because Coulomb force was discovered long before the nuclear force. So in that case, historical perspective, in the perspective of history, it was slightly different than the nuclear force. It's thing was quite different. So we knew the Coulomb force and we studied the hydrogen atom problem. So that led to the discovery of quantum theory. In case of nuclear force, it's just the opposite. We knew quantum theory and we studied neutron proton scattering. So that leads to the discovery of the nuclear force. So it is just different. So you have to appreciate these things, why it is so. And we just solved the deuteron problem, just like as we solved the this hydrogen atom problem, and that leads to this these equations ultimately. So I think it's in the next slides. And what exactly is an isospin? So it is a charge state of a, it's convenient to introduce another quantum number for describing the charge state of nucleons. So that is also important. What exactly is this and how it's different from the ordinary spin? So when we solved this Schrödinger equation, only thing that is different was in case of the reduced mass, it is half of the mass of the nucleon, while in case of the hydrogen atom problem, the reduced mass is almost the mass of the electron. So if you solve it, nobody is going to ask you for the deductions. So you just remember the final this thing. So it is W is equal to V0 minus H cross square K square over M. So from here you can find out whatever some problem asks. So it is like that. I think some of the problem sets also have this kind of problems. So you have already gone through this at least once, I believe. So you don't have to do this for your exam. So these sort of, so at least you understand how it comes about. So how these transcendental equations, how you solve it, and get to the ground state and the excited states of the Deuteron. So there is technically no excited state of Deuteron because it is so loosely bound. So obviously any excitations given to it, it will immediately break up. So there is no bound excited state of a Deuteron. Okay, so these are complicated equations which are not required for your exams right now. So the well depth, you can remember this at least. So the minimum well depth that is required is this. Now comes the different states that we studied. So since the net wave function has to be antisymmetric, so if you have a triplet state, then the charge can be either triplet, then the angular momentum will be odd. So the net, if you multiply, triplet is symmetric, and odd is asymmetric. So ultimately, if you multiply the three, so it will give you an antisymmetrized wave function, and a typical term is 3p. So if L equal to 1, it is a p state, and if it's triplet, so spin multiplicity is twice, its sigma is equal to twice s plus 1, so it is 2 into half plus 2 into 3 by what is it? 2 into 1 plus 1, that is your 3. So it is spin multiplicity is 3, and if it's 0, oppositely these nucleons have opposite spin, so it is 0, 2 into 0 plus 1, so it is singlet, 1s state or 1p state, and the triplet state is 3p state, 3s state. So these are some of these states. So might be asked one number one question. If it's what exactly is a spin triplet, what exactly is a spin singlet, what are the typical terms? So maybe one. And the numbers given for such questions may be just 1 or 2 at most, not more than that. So then comes this nuclear force. In addition to the central part, it also have a non-central or tensor part. So that makes the nuclear force very complicated. Also, the Deuteron is cigar shaped. So ultimately, you will see the quadruple moment and the magnetic moment of the Deuteron. So these are the typical terms that are involved in the nuclear force. So you see it's how it's like R cross P can be a term, because if it's minus R times minus P, so it remains same under reflection. And the terms that are involved are sigma 1 dot R, sigma 2 dot R. This corresponds to two different nucleons. So you see for the Deuteron, it's a mixture of S and D states. Then you have these Yukawa and mesons, and I gave you an example that if you try to stick to Scotch tapes, so it's more or less like the nuclear force. So if they are very far apart, they do not attract each other, but they come very close to each other, then they are stuck in such a way that it requires a lot of energy to separate them. So the nuclear force is something like that. Now, initially, people try to the messenger, the scientists thought that there must exist an entirely new and as yet undetected particle that actually does the exchange between the nucleons. So initially, Yukawa gave the name. The name given to that particle was meson. So it is a mid-weight particle. So that's why the name was meson. And initially, it was found that there is a mu variety, so which is 200 times the mass of an electron, and later on it was found that there is a higher version, the pi meson, which decays into the mu meson. So that is a higher variety, so 264 times the mass of an electron. So these mesons, these pi meson, these are actually the particles which gets exchanged between the nucleons to form that nuclear force. So the mesonic charge that was found out to be F, and the generalization to the normal equation goes that there is this third term enters, that mu square V. So that gives you the elementary static solution of the electromagnetic equation is the Coulomb potential E by R, and the corresponding static solution of Yukawa's equation is F e to the minus mu by R. So basically, then this leads to short range forces which vanish at a distance of 1 by mu. So you have this universal constant mu of the order of 0.3 to 0.5, 10 to the 13 centimeter inverse. So then now till now, any questions, anybody?
No,
All of
sir.
you are listening properly, right? Okay.
Yes,
So
sir.
do you is it okay that if I go like that, is it doing good to you? I mean, this revision.
Yes, sir.
Yeah.
Yes.
So you are recapitulating what actually we covered and what are the most important things for your exam. So
Yes.
you can understand, right? So if I'm saying, do you I mean, do you understand? I mean, I'm trying to convey what are the most important things for your exam. So are you? Maybe you can note it down in some piece of papers also, so that while you revise, you do not forget. But obviously, when you go through the lecture notes, since it's the same thing that I'm showing, so obviously when you go through it, I believe that you will remember what I said in this lecture, because it will be very fresh. Anyway, if you forget, don't worry. Next lecture also we will discuss such things. And the next, I think before exams, I may have another 2 lectures. So I will discuss this sort of things only, so that you give your exams in a proper way. So these are the different states that I mean, discussed. So you have this sigma is the spin multiplicity, S is the angular momentum, and J is the total angular momentum. So the typical terms that comes out are like for J equals 0, L equal to 1. So if it's equal to 1, then it's a P straight. And if it's J is equal to 0, so you have in the suffix you write 0. And the spin multiplicity, if it's 1, since J equal to 0, J is equal to L plus S. Then if it's J equals 0, then S has to be 1. So if it's S has to be 1, then it is 3 into 1, 2 into 1 plus 1, so it is 3. Similarly, the other terms. So these are the typical terms for J equals 0, J equals 1, J equals 2. So these are the typical terms in nuclear physics. Then we go to magnetic moment of the deuteron, and you have seen that if you just add up the proton and neutron magnetic moment, it does not give the total magnetic moment of the deuteron, because there is orbital contribution involved. So you have this M equals mu p sigma p mu n sigma n plus half L. So that's why this difference comes if you just add up the total magnetic moment. So you have seen that if you add up mu p plus mu n, it gives 0.880, and experimental value is 0.857. So we tried different types, 1p1 state, 3p1 state, 3d1 state, and ultimately we find that it's not a single angular momentum that the proton and neutron are involved in. So there are 2 different angular momentums of the deuteron. So that is S state and D state, L equal to 0 and L equal to 2. So during some time, the deuteron stays in L equal to 0 state, and during the other times, it stays in L equal to 2 state. So that gives the total angular momentum, the magnetic moment is 0.857. So you see that this 4% of the time, it stays in D state, and the other 96% time, it stays in the S state. So that is important. So I think this one is important, and you might be given some problems to find out this probability as 0.040 for the D state, and the other part 1 minus that for the A state. So this might be an important question. So what are the different probabilities of the deuteron to stay in S state and D state? Then comes the quadruple moment. So it is kind of these complicated equations. So you are obviously not going. The only thing that you should remember that the size. So if the charge is extended in the z direction, the quadruple moment is positive. So you have a positive quadruple moment. It's a prolate in shape. So this is an important thing for deuteron to remember. These equations nobody is going to ask. I think you have gone it at least once. Sorry. The things, and then comes the binding energy. So this nuclear structure, nuclear saturation. The most important thing is that you have to remember what is the binding energy of nucleon. So it is about 8 MeV per nucleon. So you have the middle part of, so y-axis is binding energy per nucleon, and x-axis is A, the number of nucleons. So you have in the middle of the curve, it's nearly constant at a value of around 8 MeV. So You might be asked, what is the binding energy of a nucleon? You have to write 8 MeV per nucleon. So you might also be asked why it drops at small a and why it drops at large a. So that is also important. So in small a, since there are less number of nucleons, so full binding is achieved only when nucleon is surrounded by other nucleons. But if there are small number of nucleons, every nucleon is not surrounded by other nucleons, so that reduces the binding energy. And in the larger side, there is Coulomb repulsion acts between every pair of protons, so that reduces the binding energy. So and it increases at z squared. So these are in the picture of the binding energy curve. You might be asked questions about this. Then. So, and what are the magic numbers? So you have one particular nuclear feature which had considerable influence in this way is you have is the existence of the so-called magic number. So what are the characteristics? Very distinct properties, and you have the magic numbers 2, 8, 20, 28, 50, 82, 126. You have to remember these numbers. So this such nuclei have much higher cosmic abundances. Number 2, nuclear binding energy is the greatest at magic number nuclei, and nuclear quadruple moment changes at magic numbers because you have closed shells and then it changes to another shell, so you have this quadruple moment changes sign. So from these things, nuclear shell model came up. So what exactly is nuclear shell model? So it is a mean field model. So you put one nucleon outside of the closed shell, so that falls into the potential of created by all the other nucleons. So you have a particle in a potential well. So this potential is representative proportional of the nuclear density. So it's the similar as the nuclear density. So the shape of this potential would be similar to the nuclear density. And here it's very physically important. Might be asked some physical questions. So I mean, what exactly is the nature of the, or I mean, whether the orbit picture is useful, because it's a complex many body problem and a single particle in a potential well, and it's dense and very complex. So how come this orbit picture comes about? So you have to remember that Pauli's exclusion principle plays an important role here. So basically there may be several number of orbits, but the number of orbits, that is the picture B. So it's kind of random motion, classical picture. But in quantum mechanically, there is Pauli exclusion principle. So the number of orbits are severely limited. So ultimately the actual picture is picture A. So since it severely limits the possibilities for collision, so you have an orbit picture. You might be asked, since the nucleus is so densely packed, how can you think of an orbit picture in a nucleus? So this might be an important issue. So there are these are the levels. I think I have discussed a lot about these levels. So initially it's the left one, and then once you incorporate the spin orbit part, you have the right one. So you might be asked, given a nucleus, say A is equal to 28. So what will be the shell model configuration? So you have to write 1s2, then 1p 3 by 2, then 1p half, then 1d 5 by 2, then 1s half, then 1d 3 by 2, then 1f 7 by 2. So that completes up to 28. So you might be asked, what are the different levels that are involved to for this particular nucleus? You will be given, say, A is equal to 32. So give the shell model configuration. So you have to write all these levels serially. So that you have to count the number of nucleons, because you cannot, if it's 50, then you can see that it is what is that? I can't see it. So 1f 5 by 2 or something like that. But if you are given more than that, then after that there is, if you are given 60, then you have to include that level 2d 5 by 2 also, just above 50. That level, because another nucleons might come from there. So you have to remember what, because 1p half. So 1p half means 2 into half plus 1, that is 1 plus 1, that is 2 nucleons. That is 2 protons, 2 neutrons. 1p 3 by 2, that is 4 neutrons, 4 protons. So likewise, you this is very, very important for your exam. So you how you I mean, fill up the different shell model states. So, but you don't have to remember all the levels up to 184. It is difficult. So I would say that you at least remember up to, say, 30 or 40 at most. So like that. So at first you have the magic number 2. So you remember 1s half, 1p 3 by 2, 1p half, 1d 5 by 2, 2s half, 1d 3 by 2, 1f 7 by 2, 2p 3 by 2. So like up to that, that is okay. Just above 28 or slightly more than that. So that will be sufficient for you for your exams. So this way the shell model structure comes up, and here how these levels, this capital N is equal to 2n plus L minus 1. So how these different shells. So that is first shell is you have these shells are here. It's given this number N is given in the middle of two levels. You have this N 1, 2, 3, 3a, 4, 5 like this. These are the different shells. So these number of shells are given here in this table. So you remember that. So this is important. This is very, very important for your exam, how you fill up this shell model states. So it is a great success of the shell model. And then you have this Smith lines for the magnetic moments. And then you have these violent fluctuations in unequal when the A number increases. So that gives rise to nuclear collective model. And you have these different expressions, whether it might be as it's like a charged liquid drop. So either the radius is, nucleus is permanently deformed, or it is a spherical, which the deformation evolves in time. So time dependent, either time dependent or time independent. So that goes for lecture notes 1. Now I will just quickly go to lecture notes 2. Just a moment. This is PDF. Just a moment. Lecture notes 2.pva. No, this is not the one. 2. Everybody can hear me, right?
Yes, sir.
Yeah, so I'll just switch over to lecture notes 2, so that if we finish next lecture, you can ask again, revise the whole stuff, and you can ask some specific questions that you may have. Just a moment. What happened? Stop presenting. Then present now, a window. Just a moment. Opening. Now it came. Can you see the screen?
No, sir.
You
No,
can't
sir.
see the screen yet. Just a moment. Now you can see it, right?
Yes, sir.
Okay. So after the nuclear collective model, then comes the nuclear decays. So for is the beta decay, which is very nice. And what actually led to the discovery of beta decay? Because it was the continuous spectrum of the beta spectrum. Because initially people thought that it's 2-particle initial state, 2-particle final state. People didn't think about this third particle. But this continuous beta spectrum was so confusing. Niels Bohr was even prepared to abandon the theory of conservation of energy to explain that. But actually what Pauli, the genius of Pauli, that gave rise to the prediction of a third particle, which is the neutrino. So that is important, the most important thing in beta decay. And so you might be asked, what is the typical ratios for the 4 forces? The nuclear, electromagnetic, weak, and gravitational. So it is 1:10⁻², to 10⁻5, to 10⁻39. That is important. And the beta decay process can be generalized into these 3 types: neutron going to proton, proton to neutron, and electron capture by the proton. So these last 2 will take place only inside the nucleus, and the first one can occur in free space, because the neutron mass is larger than the proton, so it can freely decay to proton. But since the proton mass is lesser than the neutron, it can only occur inside the nucleus, where the proton has some kind of kinetic energy, so its net mass is more than the neutron, then only it can decay into a neutron. In free space it cannot. Okay, then this is beta decay. These are the typical 3 beta decays. You are not going to be asked this deduction, so you can forget about it. Only thing, some simple energy momentum balance that will give rise to the what is the momentum of the beta decay. I think I've given some problems, so practice it well. So this is, it drags the electron towards itself, the nucleus, and it pushes the positron away from it. That gives rise to shifting of this momentum towards higher or lower side. And then these are all deductions, not important for you at present. I think you have gone at least once after the lectures. What are other electrons? That is important. What is parity? That is very important. So what exactly is parity? So I have discussed a lot that mirror reflection followed by 180-degree rotation, that is parity. So it is basically a space inversion. So right-handed things are converted into left-handed things. Some basic questions might be asked, what exactly is parity? So you have understood this experiment, that and the mirror reflection of the experiment. So that is important. You have already understood this. Then nuclear electromagnetic interactions, not important for problems at this stage. Only thing you remember that these electric transitions are 1 order of magnitude in magnitude more than of the same multipolarity. That is important. Here, the roughly successive multiple transitions are an order of magnitude less probable than the preceding one. This is important. Internal conversions, and then the drop model, the liquid drop model. So I have given you an example, just like in HOLY, the water balloons, and the nucleus is something like that. So you have these different terms. The volume term, these are important volume terms, and once you have this binding energy term, so you might be given some problem that these values might be given, this all these masses, you have to figure out what is the mass of the nucleus or what is the binding energy of the nucleus. So you have this whole formula, so you can find out. Then comes nuclear reactions. So what exactly is a nuclear reaction? So what are the basic characteristics of what we can understand, what we can observe, basic things. And what is the Q value? You might be given a nuclear reaction, you have to would be asked to find out the Q value of this particular reaction. All the masses will be provided, so you have to understand the entrance channel mass minus the exit channel mass minus the excitation energies. That will give you the Q value. What exactly is the Q value? Okay, so, and this is the cross section. You might also be given to find out the cross section. If you are given this data, what is the cross section of the nuclear reaction, and what is an impact parameter? That is important. You might be asked, what is the time scale of a direct reaction and a compound nuclear reaction? That is important. This you have seen. What maybe at lower impact parameter, which reaction is important? Is it elastic scattering or it's a multifragmentation? So you would answer that at very low impact parameter and very high energy per nucleon, multifragmentation. It might be asked that at what energies and impact parameters, elastic scattering and multifragmentation, what is the probability of all these things? So you will see at high impact parameters, elastic scattering is more probable. At low impact parameters, multifragmentation is more probable. At higher energies, multifragmentation is more probable. At lower energies to higher energies, elastic scattering is more or less same. So you have different reactions. And these are some of the things. What are the impact parameter might be used for some problems. So find out the impact parameter. Then this potential scattering theory, obviously your quantum mechanics course has already covered. So I don't think some questions might be asked out of it, because it will be asked in quantum mechanics 2, I think. This quantum mechanics 2 is in this semester, right?
Previous
Is
semester.
it right?
Semester 2.
What?
was in semester 2, sir.
In this semester? This semester, right?
No, sir. It was in semester 2.
In semester 2. So obviously here, so you might be asked a simple question. So what is a phase shift? So basically, so you see that attractive potential pulls a wave function in, whereas the repulsive potential pushes it out. So what exactly is a phase shift? So I think up to this should be okay for you. So this is a complete revision. So you can see that in 1 hour, I have completely revised the whole nuclear physics course. So you can also do it for yourself. This whole lecture notes, you just go through it within, I took it 1 hour. So for your case, it might be 2 or 3 hours. So you can go through the whole lecture in 2 to 3 hours. Similar thing for the problems also. So I will discuss all the problem sets in the next lecture. So remain in the class, so that will help you a lot for your exams. So are you feeling comfortable with nuclear physics course?
Yes, sir. Very much.
Okay.
Yes, sir.
So everybody, I want to hear from everybody. Just be honest to yourself, because if you do not feel comfortable, then I will discuss more in the next lecture so that you feel comfortable. So everybody, all of you feeling comfortable with the nuclear physics course? Are you confident that you will do good in the exam?
Yes, sir.
Yes, sir.
Okay. Okay, just so practice well. So I won't take much of your time. So you have to prepare for your GATE exams. So good luck for your GATE exams. So I will wind off here. So in the next lecture, in next Wednesday, I will discuss all the problem sets. And also, if you have some questions from the lecture notes, please let me know. So I will explain that more carefully. Okay?
Okay.
Okay, sir.
Thank you, sir.
So
Thank you, sir.
okay. Goodbye. Good luck and good luck for your GATE exams. And please help your